Mohamed, we apologize for this technical issue.
Yeah, no problem. These things happen, so.
I think we are live now.
We're live? Okay. So let me share my screen first. So I think we are live now. Hello, everyone, and sorry for this delay. We will start. I think we'll not waste a lot of your time and just start right away. So welcome to this new MoroccoAI webinar. We have the pleasure to have with us Dr. Mohamed Amine Seddik, who is an AI lead researcher at the TII, Technology Innovation Institute in Abu Dhabi, the United Arab Emirates. And today he will be talking to us about using and taking advantage from random matrix theory to unlock generative modeling. So let me read to you a biography of Dr. Mohamed Amine Seddik. So he's an AI lead, yeah, as I said, researcher at TII Abu Dhabi. He obtained his master's in data science and machine learning from the Institut Mines Telecom of Lille-Douai, with the final year completed between Telecom Paris Tech and ENS Paris-Saclay in 2017. He then completed a PhD in signal and image processing from Centrale Supélec, CEA, and the University Paris-Saclay in 2020, and conducted postdoctoral research at École Polytechnique in 2021. He also worked as a researcher at the Mathematical and Algorithmics Research Lab within Huawei Technologies France in Paris in 2022, and his main research interests include machine learning, deep learning, random matrix theory, random tensor theory, and generative models. Without further ado, I'll leave the floor to you, Dr. Mohamed Amine Seddik, and thank you again for accepting our invitation.
Thank you, Ridwan, and thank you for the invitation. So
yeah, you can share your screen.
Let me share my screen. So I guess you can see my screen now.
Great, thanks. Yes.
Great. Okay, so yeah, thank you so much for the invitation. It's my pleasure to participate in this Morocco webinar series. So as Ridwan said, I will be talking about using random matrix theory, so to understand a very basic generative model, which is in fact a linear one. This is the most basic model that we can have to generate. And the idea is to try to understand theoretically what are the performance of this model when it's trained on a theoretical model, basically. So the outline of my presentation will be as follows. I will start by just recalling some introduction from about large language models, and basically the state of the art about these models, and then the second part of the talk will be about the specific model that we will be basically analyzing. So it's just a linear model, a linear toy model for theoretical purpose, and then I will close this presentation by some takeaway messages and important conclusions. So I guess everyone knows what ChatGPT is now, and I mean, even everyone uses ChatGPT now, so it's very very popular. And the main reason why these LLMs, these large language models, became so popular now is that they are based on what we call foundational models. So they are models that we can train in a self-supervised pre-training manner. And by self-supervised, we mean that we can train them without having any supervision from human on text from the internet, basically. And we have access to a lot of text And the way these models are trained is just by basically predicting the next word given some sentence. So in the NLP terminology, basically what you start doing is you take your text and then you break it down into smaller units that are called tokens. So basically each token will be a word or a subword of your text, and then you represent this word or subword by some number. And then what you do is that you convert these numbers into high-dimensional vectors, and this is called embedding. So for instance, if we take this sentence here, so in the different colors you see the different tokens basically, and the way LLMs or these foundational models are trained is that you give it some context, some number of tokens, and you ask it basically to predict the next token in the sequence. So formally speaking, we have basically a corpus or a data set which has a vocabulary size. So K, it's basically the number of possible tokens in your vocabulary. And what you do in practice is that you train this cross, or you do a classification problem by classifying, by predicting the next token in the sequence. So you have basically each I is a context embedding. So it's a matrix or a sequence encoding your context, and then you apply to it some representation phi, which will be basically described by what we call transform architecture, and then you predict the next token by optimizing this objective. So from this objective, we see that this phi is a very nonlinear mapping, which makes this objective a non-convex optimization problem. So if you want to analyze basically the behavior of this model, it's very hard given the complexity of the optimization problem. All right. So, and what made these LLMs very powerful is, so basically there are three main points. The first one is the architecture. So maybe some of you heard about this paper, Attention is All You Need. So this is basically one of the most important components of LLMs, which made them very powerful. So the idea of this model is that so they rely on what we call attention mechanism. So basically, for encoding the sequence, what we do in practice is that you build some network which is a sequence to sequence model, and the way the sequences are transformed is by computing some attention. So by attention, we mean a weighted sum of the sequence that is given as input. So here you have what we call the value, which is a linear transformation of your input sequence, and you multiply this by some attention mechanism, which basically tries to understand, to weight the different component of your sequence, and the output is computed by this weighted attention mechanism. So for instance, if you take this A, so the attention being identity, you get a standard MLP model, but having this attention mechanism gives you more powerful models like in practice. And this mapping phi that I showed before is just this attention, and you keep only the last component. So you apply many attention blocks, and you keep only the last vector of this of the matrices you get of the sequence. So this is one thing, and so the first component was architecture. The second one is the fact that we have this self-supervised pre-training, so which gives you access to the whole internet basically to pre-train the model. And the last one is what we call scaling. So this came with the fact that if you keep increasing your data set, the size of your data set and the number of parameters, then you get more and more powerful models. So this is completely empirical results, which is based in some empirical formula, for instance. So that predicts basically for different data set size and different parameters, like the dimension or parameter size of networks, predicts the behavior of the loss function, of the test loss function for these models. And in terms of theory, what we want, or what we want to do, is basically be able to have some theoretical framework which can predict this kind of formulas, but theoretically, like by putting some assumptions on our data, or like having some reasonable assumptions on data and analyzing this optimization problem. What we want ultimately to have is an understanding of the behavior of the test loss function in terms of different parameters. So basically predict this kind of formulas. So as I described, this problem involves high dimensions. So both the number of parameters that we are dealing with and the data set size are really large, and estimating. So when we tackle the problem of estimating the loss function, so the loss, like estimating the test loss of this model, is basically a scalar quantity. So it's just some scalar quantity, it's just a number, which is a function of random matrices. And these random matrices are basically the parameters of the network and their relationship to the data set that you're using. So we have data set, you can represent it as a random matrix, and then what you want to predict ultimately is something which is a function of these random matrices. So this is where basically random matrix can be applied. So here it's very general picture, but what we'll be doing next is try to apply this to a very simple model. So in fact, we will use, so we suppose that we have some data sets. So here I'm taking, so as I presented in the beginning here, instead of taking the sequences, I use the representations of the sequences as my data, right? So we suppose that this HIs, so we have data that are given by the representations of each sequence. You can think it of as an embedding of the text that you give to ChatGPT, for instance. So you give it some prompt, and this prompt is represented by the embedding representations of the network, and these HIs will be these embedding vectors, right? So we suppose that we have this data, so we have n of them, and the corresponding labels, which are basically one-hot vectors that encode the next token of this sequence. So HIs will be the representations of the text of each like text in our data set, and YIs will be one-hot vectors, so they are vectors of dimension k, the vocabulary size, where they are like, they have zeros and one at the position of the next token, basically. So we suppose we have this data, and instead of using this complicated like cross-entropy loss function, we suppose that we have like just an L2 loss function. So so basically you compute the average square loss between labels and input with some regularization parameter. So and so if you take the gradient of this and you write a solution, you get that this W, so the weights are a function of your data of your of X and Y as follows. So you have this Q function, which so we will see later it's called the resolvent matrix. So we see that from a random matrix point of view, this object is very interesting. And as you can see, the weights are given as a function of the data that you have here. So given some, now if we have some prompt representation, which is some vector of that comes from the representation of a network, then we can compute basically the forward pass as just projecting the weight matrix onto the given prompt representation. All right. So to do the theoretical analysis, we basically need to have some assumptions, some statistical assumptions on the representations, on these xi's and the yi's, and we need to have some relationship between those. So for that, we suppose that we have here context like vocabulary size case will be the number of classes basically, or the number of tokens that we have. And the other assumption is that I make here is that we suppose that we have a number C of possible contexts. So what I mean by that is that you can basically write a sentence, and this sentence can be one example of many others, like many other sentences that have the same meaning. But if by changing only like the words by their synonyms basically. So if you have some sentence, I went to Paris, then if you can change like each word by its synonym, and it will has the same meaning. So I went to Ile-de-France, or I went to I don't know. So if you change only the synonym of each word, then basically this sentence will have the same meaning. And the assumption that I put here is that we have a number C finite of possible contexts. And so each context is has a proportion PA here in the data set, and each representation, each I that comes from the representation of the model basically is represented as a mean vector plus some noise vector Zi, which is just a random vector. So the Zi basically will model all the possible sentences that have the same meaning as this mean mu I, right? And the way we sample the next, so the labels, so the next tokens basically, we suppose that the next token is conditionally, so it's conditionally dependent on the class or the meaning of the context Hi basically. So we suppose that we have this conditional probability of the next token, which I call PAG here. And what we want, basically, we want that our generative model to learn these conditional probabilities. So if I have some generative model which can learn these conditional probabilities from the data that I give it that are sampled from this distribution, then I have a generative model basically that can predict or generate the same language as the one I used for training it. All right. So again, for the forward pass, what you can do given some new point which is independent from the dataset, of course, you can compute the forward or the prediction, the probabilities for this model by computing the vector matrix product between the weights and the given prompt. So having said all these assumptions, what we want to estimate, so we want to estimate the test error of this model, of this very basic model, as a function of the different parameters of the statistical model that we have. So the parameters basically are D, which is the dimension of the representations, n is the number of samples, and these statistical parameters mu I, pi, and gamma, which is the regularization parameter of the model. So we want to basically to write a function of these parameters which can predict test loss of this model. All right. So for that, what we will do, we use basically random. So we use tools for random matrix theory. And before I give you the result, like of this formula, basically of the different parameters, I will just introduce some key questions from some key notions from random matrix theory that are essential to understand what's happening basically in high dimension. So here, let's take an example where we have data that are some Gaussian vectors. So we have n data points in dimension d, and each data point is an independent Gaussian random vector with 0 mean and covariance sigma. Okay. So as some of you may know, in classical statistics, if we take the number of samples to be very, very large, and we keep the dimension of the samples fixed, so we have fit d that is fixed and n going to infinity, we can show that with maximum likelihood, if you take the sample covariance matrix, so it's an average sum of xi transpose, then you have the almost sure convergence of the sample covariance matrix to the true population covariance matrix. So C hat will converge almost surely to this sigma. Whereas in the what we call the RMT or random matrix theory regime, if you let both the dimension and the number of samples go to infinity, you have what we call a curse of dimensionality. And by that we mean that if you compute, for instance, the difference, the norm of the difference between the C hat, so the sample covariance, and the true population covariance matrix, then this difference does not converge to 0 anymore. All right, in the spectral norm term. And what random matrix theory does basically is it predicts the behavior, the spectral behavior of this of random matrices. So in this case, of the sample covariance matrix. And in fact, what we can show is that if you look at the distribution of the eigenvalues of these random matrix, you will see that instead of being 1, so if you take sigma being identity, for instance, you should have like only one eigenvalue at 1. Instead of having only one eigenvalue, you will have a spreading of eigenvalues, which is described by a specific law, which is called here the Marchenko-Pastur law, right? So it's a very old result. It says from 67, which describes precisely how the eigenvalues of a simple covariance matrix behave in high dimension. So if you take your Python, like a Python program, and you write exactly, so you simulate this and you keep increasing the dimensions of your matrix and looking at the histogram of the eigenvalues, you will see that it will converge to something that is close to this form. All right. So, and to prove this kind of result, we can rely on random matrix theory. I'm not giving a lot of details here, but basically, if you, as I said before, this matrix is a key object in random matrix theory, and actually it gives you access to a lot of information about the behavior of this sample covariance matrix. In fact, if you take the case of classical statistics, so we have the convergence of this Q to sigma plus Z identity minus 1, but in the random matrix regime, so we can show that this matrix can converge in some specific case, in some specific sense. So we see that it's equivalent to some deterministic matrix. So what we call by deterministic equivalence is that you have the convergence of any bounded linear form to the deterministic object here. So random matrix theory gives us this kind of result that there is an equivalent of this random matrix Q to a deterministic one, which is given by this expression here. So it's sigma divided by 1 plus delta, where delta is given by this quantity. And this delta basically goes to 0 if only n goes to infinity and the dimension is fixed. So it's consistent with the classical statistics, basically. So what this result tells us is that in high dimension, the behavior of the random matrix, like of the matrix that we are studying here, is sample covariance matrix, can be biased in some sense. So we need to have this delta, this correction to understand its spectral behavior. And in fact, if you take n over d delta of minus z is an object that we call the Stieltjes transform, and it's related to the spectrum of the C hat. So this basically this object here, it's the object which can predict this spectrum that we see here. All right. So now we will get back to the problem of estimating our loss function of this generative model. So I recall that the testral loss is given, so it's a distance between the true probabilities and the ones predicted by the model. And so when we do computations using this random matrix theory, we obtain this result. So it's so we obtain that the test error will be something close to some deterministic value. So E bar test here, which is given by this expression. So I can't say like much about it, but what we can see is that it depends on the different parameters that I mentioned before. So the true probabilities P, M being the means of each cluster in my representation. You see this gamma, the regionalization parameter, and all the different parameters that are involved in the problem, right? So for instance, if I take like here I take just a toy example to generate these conditional probabilities that we will feed basically to the model to learn. So here I'm taking the example where we have k equal 3 tokens. So we have a language of three tokens basically, a context length of 4. So the number of possible contexts that you can have is k to the power L, so it's 81. And you can see all the conditional probabilities of this case. And when you train the model, you will see that it will learn something close to the true conditional probabilities, but with some error. So you can see that the predictions are not exactly matched with the true conditional probabilities. And in fact, if we get back to the expression of the weight, of the weight matrix here. So if you take the regionalization being very, very large, you get some simple model. So it's just so we can see that it's linear in this H. So it's linear in the training data. And if you take gamma being too small, then you get something like very complex model, like a complex model which is nonlinear in the data. And using like the previous result, so this result here, so you can see that we can predict, so here this is simulation versus theory, we can predict the behavior of the loss function, of the error loss function, basically in terms of the different parameters. So here I present in terms of gamma, and if you can vary also like the different parameters. So here eta will be the ratio between the dimension and the number of samples. So we can see that it can predict. And from this observation that we have before, So if you take gamma being too large, so we are basically here, then you get a simple model, and we see that it does not generalize well. So we have a poor test error for a simple model. Whereas if you take a very small gamma, you have a complex model. And so you see that you have what we call the behavior of overfitting, because the model does not achieve the best test accuracy, like test error. And there is some optimal gamma for which you can achieve. So the theory can predict basically the value of this optimal gamma, which can give you the optimal performance. All right. So now I will just conclude by some takeaway messages. So what we showed basically is that RMT, this random matrix theory, can provide us with tools to assess the behavior of these type of algorithms in high dimension, when both the number of samples and the data dimension are large. And in fact, we have seen that through the simple example of linear generative models. And by we have seen the example of providing the characterization of the test error, for instance, here. And you can do many other, depending on the problem that you want to estimate. So you can have some tools which can predict the behavior of the quantity that you are interested in. So beyond this example that I showed here, there are many applications of random matrix theory in a wide range of machine learning problems, such as kernel methods, large neural networks, so on, what we call neural tangent kernels, so NTKs. There are also applications in the case of implicit convex optimization problems. So here, the problem that I presented is when the solution is written explicitly in terms of the data, but you can have situations, if you take the cross-entropy loss function, for instance, where the weight relationship between the weights and the data matrix can be implicit. And in this case, there are some tools to address this problem. And also, there are many other applications to many other machine learning settings, such as unsupervised, semi-supervised, and transfer learning. And for that, I suggest you to look into this two main resources. So there is this book from my former supervisor, PhD supervisor, who give a lot of tools from random matrix theory to address machine learning problems. And there is also this tutorial which was presented at ICML, which gives a very huge literature about the applications of random matrix theory to machine learning problems. All right. So I think that was all for me, and I will be happy to take any questions.
Thank you very much. Thank you very much, dear Mohamed Lamine. We do actually have questions. Yeah, let me start by. So we do have a various number of questions. Some of them are probably basic. Some of them are more advanced. So let me start with maybe the simplest ones. So you mentioned curses of dimensionality. So can you maybe explain it just in simple words for people who are not familiar with the
So a simple explanation is, for instance, if you let's say we live in a two-dimensional space, and I ask you to throw two pens, for instance. You have two pens and you throw them in two-dimensional. Then if you keep repeating this experience, then you can have basically the possible angles between the pins. So you can hold all the possible positions. And if you repeat the same experience in high dimension now, you will see that with high probability, the two pins will be orthogonal. All right. So this means that the notion of distance in high dimension is not the same as in small dimension. So even points that are far away from each other in high dimension will be as far as the closest ones, right? So this is like a way of explaining what happens.
Yeah, thank you. In one of your first slides, I think so, the person who asks about the vocabulary size. I think if I remember, it was K.
Yeah.
Maybe. So so the question is it like predefined, or you choose it, or
Yeah,
depends on the
so
problem?
this is defined by the way you tokenize the text. So this tokenization, so this process of converting your texts into tokens. So you need to choose like how to tokenize basically. So for instance, in this example, you can see the word mathematics is divided in two tokens. So there is a word math and why we, for instance, in this example, you use the word math as a specific token because you can write mathematics or math, so in a sentence. So you need to like it's more. So the way you tokenize your words gives you like this vocabulary, like the vocabulary size defines this vocabulary size basically. So it's the number of unique tokens that you have.
Okay. Next question is the following: what is the intuition behind that formula of scaling law?
Yeah, so the intuition is so they started by basically by writing the laws as like it was completely phenomenological. Like you compute like you train a lot of networks at different sizes and different data set sizes, and you try to fit a function on that. So this was I think this is how they did that, obviously, but there is no theoretical result which shows that this formula is the right thing.
Okay.
Yeah.
So maybe for the person who asked the question, the reference, right, that you put in
this
the
is the
footnote
reference.
is the one they need to check.
Yeah.
Okay. Next question is: can you say a word about the computational constraints to run LGM?
So for this linear model is not something that you can like really do in practice because it's completely theoretical, like a theoretical model just to try to gain some insights into how these language models work. In fact, if you take a transformer and you linearize all the layers, then it will boil down to this problem, right? So the idea is to try to first do something with the linear model and then to try to complexify a bit like the different components and see how we can generalize this to nonlinear models.
Another very specific question: where can we find papers to find optimal gamma? Maybe related to the end.
Yeah. So here you can check this put that has like a lot of so it's the same kind of results that I showed here, but applied to many other problems. So yeah, this is a good reference. For this.
Okay, so this is a nice reference for people who are interested in random matrix theory and other aspects.
Yeah.
Now we move to sorry.
Yeah, this book has like an introduction to random matrix theory part, which is very, I think, very general. That can apply to other problems in machine learning, and then specific chapters apply to machine learning. So I think it's a good reference.
Okay, and do you think this is a good starting point for someone who is interested in?
Yeah. Okay. I definitely recommend this book.
All right. So now we'll move to more like very general questions. The first one is, how do you see the future of LLMs? Are there any scientific breakthrough you anticipate in the future?
So the current trend is what I showed here in the beginning, is this kind of scaling laws. So basically, people believe that as we increase the data set, as we increase the number of parameters, then these models get more powerful, basically. So maybe a shift of paradigm is to try to build smaller models that have the same capabilities of these large models, and like try to work out, so to do some research in this direction, because I mean, for training these models, if you take the example of GPT, of Falcon, for instance, the TII released this 180 billion model. It costs a lot of money to train these models, because you need to use like a lot of GPUs. For instance, for Falcon, it used 4,000 GPUs to train. So it costs a very, very lot of money. And I think for the future of AI, we need to reduce this. We need to find a way to have like smaller models with the same capabilities.
All right, thanks. Another question is, what are the main challenges of building LLMs? But I think you already answered some of this question, but I don't know if you have anything else to add.
The challenges is the size, of course, and there are also other challenges related to safety and reasoning. So for that, I recommend, for those of you who didn't watch, there's a video from Andrei Karpathy, which was released like a few days ago, and they recommend for each one of you to watch it. And I think it's like he gives a lot of insights about what's happening and could happen in the future. So
yeah, I recommend it too. Excellent video. So yeah, for the sake of the time, I'll take just one very last question. How your work is related to Falcon? I think since you work at TII, maybe this is
actually. I joined TII 1 year ago, almost, and I wasn't really involved because the team who worked on that started before. But still, like we continue to work on these models and try to have more powerful models that may come after these models that were released. So for my side, I work mostly on the theory side to try to work on explainability and try to explain the performance of the models. So yeah, there is like other teams which work on these Falcon models. Yeah.
Okay, thank you. I think in the breakout session they'll have more time to ask you about details of your work and maybe even ask you about TII, etc. So yeah, please join me to thank again Dr. Mohamed Amine Seddik. Thank you very much for this excellent presentation.
And thank you all.
Yeah, sure. And now it's time to move to the breakout session. We have two sessions. You will see them in your screen. One, it's an Ask Me Anything with Dr. Mohamed Amine Seddik, where you can ask our speaker any question you have, or even ask him about also how he moved to France, how he went to United Arab State to work at TII, etc. So not just questions about the talk. And we have another breakout session, another room where you can network and discuss your AI project. But before this, I will just start